We are in chapter 7 and will be covering principal stresses in beams and stresses under combined loads. This is the 52nd session overall and the first session in chapter 7. We'll look at principal stresses in beams, transmission shaft subjected to torque and moment, and shaft subjected to shear and torque. These are the sessions covered in the first 4 chapters. When it comes to individual loads, we covered axial loads, torsion, and bending. These are the sessions covered in chapter 5 and chapter 6. When it comes to individual loads, we covered shear and thin-walled pressure vessels. We mentioned about individual loads. In this chapter, we studied stresses under combined loads and principal stresses in beams. In this session, we look at variation of principal stresses as we move from top to bottom in a rectangular beam. Also, we look at principal stresses in I-beams. We look at shafts subject to torque and moment and torque and shear. This session and most of the next session is on analysis. These 2 sessions are on examples, while the last session deals with summary. We deal with combination cases and principal stresses in beams in this chapter. To start with, we look at the variation of principal stresses as we move from top to bottom in a beam of rectangular cross-section. We then look at the principal stresses at the junction of the web and the flange of an I-beam. This is because the principal stress at the junction of the flange and the web of an I-beam can have values that are greater in magnitude than the principal stress in the outermost fibre. We have earlier dealt with shafts subjected to torque in chapter 3. Here we deal with shafts subjected to torque as well as moment, which can be in 2 perpendicular directions. We also look at shafts subjected to torque and shear. This concludes the discussion in this session. We have dealt with combination cases before. In chapter 4, we dealt with eccentric loading and unsymmetric bending. These involved summation of normal stress. In chapter 6, we dealt with pressure vessels also subjected to other types of loads, such as torque, axial load, and moment. Here we mainly deal with combination cases related to circular members or rectangular members. To start with, we find out the section with the highest stress. Some points, which we call critical points, are chosen within this section. These are points which are likely to have the highest principal and the highest shear stress. We find out the normal stress and the shear stress acting at this point. We then find the principal stresses and the maximum and minimum shear stresses acting at these points. As such, we find the point with the absolute maximum principal stress and the absolute highest shear stress. We discuss the case of a circular member first, after which we discuss the stresses acting on a helical spring and on a horizontal section in a dam. Near the end of the next session, we look at some examples of principal stresses in I-beams. After that, we discuss transfer of forces so that we can find out the forces acting on a section of a structure subjected to different types of loads. The next two sessions are on examples of combination cases. The notion of transfer of forces is used. One session is on circular members, while the next session is on rectangular members, largely. In the last session, we give a brief summary, concentrating on the way we have analyzed the cases of individual loads and then combined loads. The discussion in this chapter and also in other chapters is streamlined in a succinct way. We know the process of finding bending stress and shear stress in beams. We have also studied transformation of stress. So at a given point in a beam, we can find the bending stress and shear stress, and using transformation of stress can find out the principal stresses acting at that point. Find out the variation of principal stress both in magnitude and direction as we move from top to bottom of a section in a rectangular beam. Let us consider this beam with a load applied in the middle. A section at 1,1 is taken. This is the cross section of the beam. The portion to the left of section 1,1 is shown in this figure. These are the shear force and bending moment acting on the section 1,1. They are both positive. This is a magnified diagram of the portion to the left of section 1,1. We'll find out the variation of principal stress both in magnitude and direction from the point A to point A dash, thus moving from the top to the bottom. Distances of these points from the neutral axis is given in figure 5. We'll initially find the stresses at the points A, F, and then D. This is the IZZ determined. We find out the stress at point A using this moment. The stress is compressive. At A, the shear stress is 0. At F, the bending stress is 0. Using this value as V, we find out the shear stress at F. Let us now consider the point D. The value of y in this equation is 100 at D. So we find the normal stress at D. To determine the shear stress at D, we use Q of this shaded portion. The stress acting on the elements at A, F, and D are shown here. Here the element B is shown with the stresses acting on it. Sigma x is negative, tau xy is also negative, as given here. The magnitude of the principal stress is given by this formula, and the direction of the principal stress is given by this formula. Substituting these values, we get sigma 1 and sigma 2. Sigma 1 is considered the larger of these two values. Again, substituting these values, we get tan 2 theta, from which we get two values of theta. So we need to rotate this element D by 2.14 degrees to align with the principal directions. There are no shear stresses acting, and these two are the principal stresses that will act. Now consider the point D dash. The stresses acting on the point D dash are shown. Shear stress is still in the same direction, but the direction of the bending stress has changed. So we get these values. Substituting in the formula for principal stress, we get sigma 1 and sigma 2. Substituting in the formula for direction, we get tan 2 theta, from which we get two values of theta. So if this element is rotated by 2.14 degrees in the clockwise direction, then it will align with the principal directions. We earlier mentioned that we'll find out the direction and magnitude of the principal stresses in section 1.1, moving from top to bottom. The points in section 1.1 were designated from A to A dash. In the first column, these are the elements corresponding to those points. We earlier found the stresses acting at A, F, D, and D dash. The stress in A dash is opposite to that of A. Here we have determined the stresses acting on all the elements. The maximum compressive stress occurs at A. As we move downwards, the compressive stress decreases and becomes zero at F. After F, as we move downwards, tensile stresses act. The tensile stresses increase in magnitude till we reach A dash. A dash is subjected to the highest tensile stress. The variation of compressive stress in the top and the tensile stress at the bottom are both linear. While the normal stress changes sign, the shear stress does not change any sign. Shear stress at A is zero and becomes maximum at F. Again, at A dash, shear stress is zero. As we earlier found out, the variation of shear stress is parabolic from top to bottom. The second column shows the direction and magnitude of the principal stresses. The angles keep on changing continuously from top to bottom. In the third column, we have shown the principal stress that is algebraically larger. The element A is subjected to a compressive stress, which is also the principal stress. The other principal stress in the y direction has a magnitude 0. Here, that principal stress of 0 magnitude is shown because it is algebraically higher. As we can see, the magnitude of the first principal stress keeps on increasing as we move from top to bottom. The direction continuously changes, rotating in anti-clockwise. Magnitude changes from 0 to 87.5. The direction is vertical at the top and becomes horizontal as we reach A dash. This column shows the second principal stress. The magnitude of the principal stress decreases from top to bottom, from 87.5 to 0. The direction changes continuously, rotating in an anti-clockwise direction. It is horizontal at A and becomes vertical at A dash. Beam has innumerable number of points, and we can find the principal stresses at all these points. We can form lines having the same magnitude of principal stress. We consider the magnitude, not whether the principal stress is positive or negative. Such lines are called stress contours. We can also join points with equal direction to form lines. These are isoclinic lines. So, line at the top, the neutral axis, and the line at the bottom are isoclinic lines. We next discuss principal stress trajectory or isostatic lines. These lines plot the changing direction of the principal stress as we move along the x-axis. This is the principal stress trajectory of the first principal stress, and these dotted lines are the principal stress trajectory of the second principal stress. Both lines have a 45-degree angle with the neutral axis. We have a beam here subjected to arbitrary loads. We can develop the shear force and the bending moment diagram for the beam. We can find out the section with the maximum shear force and the section with the maximum bending moment. These 2 points will be subjected to the maximum magnitude of normal stress, positive and negative, acting on the beam. This point will be subjected to the maximum shear stress acting on the beam. If we take a given section, then these 2 points will be subjected to the maximum normal stress, positive and negative, acting on the section. Till now, we have considered that these 2 points has the maximum magnitude of principal stresses. This is for the entire beam, while these 2 points has the maximum magnitude of principal stresses for this section. That is the case when the beam is rectangular. It may not always be the case when the beam has other shapes. Here we will show that the maximum magnitude of principal stresses does not occur at the extreme fiber of this I section always. This is a cantilever beam. It is subjected to a load as shown. The section is this I section. Here we consider the stresses in the section 1-1. The moment acting on section 1-1 is negative. The thickness of the web and the flange is 12 millimeter. And these two dimensions are 200 millimeter. And we find out RZZ. We'll next find the normal stress and the shear stress at the points A, B, C, B dash, A dash. At the point A, the shear stress is 0 and the bending stress is given by M minus My by I, and we get a positive value of bending stress. Since shear stress is 0, this is also the principal stress. We find the bending stress at the point B by taking proportions. We find the shear stress at the point B by using VQ by IB. Here Q is the statical moment of this flange portion and B is the thickness of the web. We earlier determined that the principal stress is given by this formula. So we get sigma 1 and sigma 2 at B. We next find out the stresses at the point C, which is on the neutral axis. Point C is subjected to the maximum shear stress and the bending stress is 0. Shear stress is given by VQ by IP, where Q is the statical moment of the upper half of this I section and B is the thickness of the web. The principal stresses at C has the same magnitude as the maximum shear stress. At B dash, the bending stress has the same magnitude as B, but is of opposite sign. At B dash, the shear stress has the same value as that of B. So at B dash, we get sigma 1 and sigma 2. At A dash, the bending stress has the same magnitude as the bending stress at A, but is of opposite sign. So here we see that the maximum positive principal stress acts at B rather than A, and the maximum negative principal stress acts at B dash rather than A dash. So for a section such as an I section, if the length of the beam is short and comparatively the shear force is larger than the bending moment at a section, then there's a chance that the point such as B would have the higher principal stress compared to the outer fibers. I've dealt with combination cases before. Here we deal with a few more of them. We look at a shaft subjected to both torque and moment. A torque here is applied at E. There are forces acting P1 and P2, and there's no torque in between C and D. In this diagram, we have added two equal and opposite forces acting at B and C. These two forces make a moment, and these two forces also make a moment. So there is a vertical downward force acting at B, and there's a moment. There's a horizontal force acting at C, and also there's a moment. Due to the vertical force P1, there will be reactions at A and D. So we get RAY and RDY. Due to the horizontal force P2, also there would be reaction at A and D. When it comes to torque between E and B, the torque in a section remains the same. Between B and C, the torque in a section is reduced, and between C and D, there's no torque in a section. There will be no shear and moment between E and A. There will be shear and moment between A and D in the vertical direction. There also will be shear and moment between A and D in the horizontal direction. Here we have figure 3 again with all the vertical forces and the horizontal forces along with the torque acting on the shaft. We'll draw a diagram of the variation of torque from E to D. We'll also draw shear force diagrams for the vertical direction and for the horizontal direction. Then we'll draw bending moment diagrams for the horizontal direction and the vertical direction. So this diagram shows the variation of torque from E to D. There's no change in torque between E and B. There's a reduction in torque given by P1 into Rp at P, where Rp is the radius of this disk. So between B to C, there's a reduced torque whose magnitude is P2 into Rc. Between C and D, there's no torque. When it comes to shear in the vertical direction between E and A, there's no shear. The reaction at A will be P1 into A divided by L, where A and L are shown. Force P1 acts at B and the shear drops. The shear between B and D is P1 into L minus A divided by L. Also, there's no shear in the horizontal direction between E and A. At A, the reaction in the horizontal direction is P2 P by L. So we get this shear force diagram. This is the bending moment diagram in the vertical direction. The maximum bending moment by formula is P1 into A into L minus A divided by L. The maximum bending moment is at P. This is the bending moment diagram in the horizontal direction. The maximum bending moment is at C, and it is given as P2 into P into L minus P divided by L by formula. Here we have drawn the bending moment diagrams for both the horizontal and the vertical direction. For the vertical direction, the maximum bending moment is at P, and for the horizontal direction, the maximum bending moment is at C. Moment is a vector, and we can find out the resultant vector or the resultant moment. So consider point F. Then the resultant moment at F is square root of mf horizontal squared plus mf vertical squared, where mf horizontal is this value and mf vertical is this value. It is to be noted that with a rectangular section or an unsymmetric section, we took components of the moment in the direction of the axis on which the flexural formula was applicable. This is for moment which was not applied to any of the axes on which the flexural formula was applicable. However, with the circular section, we do the opposite. We find a resultant moment. This is because with the circular section, all axes passing through the center are axes of symmetry. So the flexural formula is applicable for any of these axes. In Chapter 3, we studied shafts subjected to torque only. In the last slide, we looked at shafts subjected to torque, shear in two perpendicular directions, and moment in two perpendicular directions. We'll now analyze such a shaft. However, we'll neglect the effect of shear. So we'll analyze the shaft for torque acting and moment acting in two perpendicular directions. Here a section of the shaft is shown. It is subjected to a torque. The inset gives the way the direction of the moment vector is obtained. One moment vector is in the horizontal direction, while the other moment vector is in the vertical direction. We find the resultant of these two moment vectors. The maximum bending stress will be at these 2 points on the radius. Using the stresses acting on this element, we can find out the maximum shear stress by this formula. With sigma y is equal to 0, we get this expression. We can also obtain this expression using Mohs circle. The stresses acting on this element is plotted as point A in the Mohs circle. At this point, let the shear stress be tau xy and the normal stress be sigma x. Sigma y is 0. So we can plot this point and this point, and as such the whole Mohs circle. OA will give us the magnitude, the maximum shear stress. The ordinates of the center is given by sigma x plus sigma y divided by 2. So here sigma y is 0. So the ordinate of the center is sigma x divided by 2. So O dash O is sigma x divided by 2 and O dash A dash is sigma x, which means O A dash is sigma x divided by 2. Now O A squared is equal to O A dash squared plus A dash squared, which will give us the same formula. Now sigma x here is equal to minus m resultant into y divided by I xx, and tau xy is equal to T into R the shaft divided by J. Y here is equal to R the shaft, and J here is 2 into I xx. We substitute these two expressions in the equation of tau max and also substitute the value of y and j as given. Then tau max is obtained as shown. We earlier found out that m resultant square is equal to m horizontal squared plus m vertical squared, which means tau max is given by this expression. So considering that the radius of the shaft remains the same, tau max will be highest where m horizontal squared plus m vertical squared plus top square is the highest. Till now, in this session, we have dealt with an I-beam where the maximum principal stress was not at the outer fiber. We found out the normal stress and the shear stress at an interior point and used transformation of stresses to find out the value of the maximum principal stress. In the case of shaft subjected to bending and torque, we again found the normal stress and the shear stress and used equations of transformation of stress to find the absolute maximum shear stress. Here we will deal with a shaft subjected to shear and torque. When dealing with eccentric loading, we summed up normal stresses due to moment and axial force to find the stress at an element. In the case of shaft subjected to shear and torque, we'll sum up shear stresses. Summing up shear stresses is different than summing up normal stresses. In the case of normal stresses, they act along the same line. In the case of shear stresses, they may not act along the same line. It needs to be remembered that shear stresses are not vectors. However, when the shear stresses act along the same line, we can add or subtract them. As we will see that summing up and subtracting shear stresses that act along the same line is enough to find the maximum shear stress. So here we have a circular bar subjected to torque and shear. We consider a section 1-1. Section 1-1 will be also subjected to a moment due to this load, apart from shear, and it is also subjected to torque. If this is the section, then along the diameter, the shear stress due to this force will be constant. The shear stress due to torque will on the radius will act as shown. Notice that the direction of shear stress due to shear and due to the torque at P is opposite and at M is same. We have earlier found out the statical moment of a semicircle and the centroidal distance is 4r by 3 pi. So we get Q. I is pi r to the power 4 divided by 4. So we get tau at the diameter. At the points N and K, the shear stress is 0. We can find the shear stress on the outer fiber due to the torque acting by using PR by J, where R is the radius. The shear stress at M adds up and as such is the maximum. At P, the shear stress due to torque and due to shear gets subtracted. There will be no bending stress at P and M. The maximum compressive stress due to bending will occur at K and the maximum tensile stress will occur at N.